Welcome back, and this next video still have something to do with roller coasters, but this time instead of having the car on top of the loop, at this point it will be at the bottom of the loop. Okay, so let's analyze what happens when the roller coaster is at the bottom of the loop. So let me start by drawing a car in a form of a dot. For example, I have the car right here, and that is traveling around the loop, entering from this position, and now it's going to go in circles along the loop. Okay, and that is counterclockwise, and it leaves the exit on the right side. So it will complete the track around the loop. So first thing is to analyze the different forces as it goes around off the roller coaster as it goes around the loop, but this time specifically at this point at the bottom of the loop. Before that, let's figure out the acceleration. So since it's going around in circle and it's uniform circle, since this is AP Physics 1, then we know that the acceleration is centripetal in nature, or it means it's A of C, which means that it's going around in circle. And it's going around in circle because of the centripetal acceleration that is towards the center of rotation. Okay, so center of rotation, and we know that this is radius r, and the mass of our object is measured in terms of m, mass m. So free body diagram, as I mentioned earlier, let's draw a free body diagram where we have a dot, FBD. So free body diagram where we have our FBD, and then let's start with a dot representing our object here in our roller coaster. So the first force is definitely our force of gravity, which is always downward. This time we have a normal force, and normal force is upward. So unlike the previous question on roller coasters on top of the loop, where both force of gravity and normal force are together or the same direction, this time our normal force is upward. Okay, so upward direction. Upward direction. Now, let's analyze the different forces acting on it. So let's analyze and apply our laws of motion. But before that, let's put some of these equations that we've been using in the past. So first one is that the force of gravity is definitely mass times g. Some of you might be tempted to write the force of friction. Yes, force of friction is mu, or coefficient of friction multiplied by the normal force. But since friction is not involved in this problem, therefore we don't really need to write down friction force. Next one is our velocity, the tangential velocity, which is 2 pi r over the period t. And last but not least, our centripetal acceleration is simply equivalent to the square of the velocity, or the tangential velocity, divided by the radius r. Now, let's summarize them or analyze all the different forces, the summation of forces along the y-axis and the summation of forces along the x-axis. If you look at this illustration, if I am going to draw this imaginary axis, this is my x and this is my y. Since this is what we call a vertical circular motion, so therefore the circle or the track is actually going on a vertical axis, so therefore that's your y-axis. Okay, so y-axis. So the y-axis forces is actually in the same direction as the centripetal forces, or centripetal force, or centripetal acceleration. So we can safely say that along the y-axis, that is your mass multiplied by the centripetal acceleration, just like in the previous video. Mass times acceleration, but since it's going in circle, so therefore that is centripetal acceleration. The summation of forces along the x is 0 because there's no forces along the x-axis. So we can definitely say that even though we know that it should be 0, but since there are no forces acting along the x-axis, so we can immediately remove our forces along the x-axis. So we'll focus on forces along the y-axis. Immediately applying Newton's law of motion, where we have the summation of forces along y equals mass times acceleration. So we can say that forces going up is positive, so that's normal force. I think there's an issue with what I said. Since the motion is within the y-axis, it doesn't mean that anything that's going up is positive or negative going down. But instead, let's put our Fg and Fn first and then equate it to centripetal acceleration. But since centripetal acceleration is going upward and it's in the same direction as your normal force, then normal force should be positive in this case. And force of gravity is negative because it's in the opposite direction as the centripetal acceleration. So that is negative Fg. Now we all know that our Fn, so we can transfer this one on the other side of the equation, where we have mac plus the force of gravity. And force of gravity, which is mg right here, so let's plug in the value. Now we can say that it's actually mac plus m of g. So we can factor out our masses. So now we know that our normal force is simply equivalent to mass multiplied by AC plus the acceleration due to gravity, g. So this will be our equation for normal force. Now the question is, what would be the acceleration? Okay, what would be your centripetal acceleration? Okay. How would you figure out the centripetal acceleration if this is your normal force? So comparing it from the different procedure that we have. Now, of course, I will say start with the summation of forces, start with the given data. But since we have already established the given data, no need to start with it. So I can say that let's use this part of the equation for letter B if we want to solve for centripetal acceleration AC. So let's say I want to solve for the centripetal acceleration A sub C or AC. Then using this, that is Fn, or the normal force minus the force of gravity, is equivalent to MA of C. MA of C. Right, so MA of C. So now let's divide both sides by M, giving us the centripetal acceleration. So that is Fn minus Fg over M, giving us centripetal acceleration AC. Now it looks better if we place our acceleration on the right side of the equation, definitely. So we'll place it here, AC, and which is Fn minus, and what is Fg? That is mg over m. Or we can simplify it further. You can stop here, or if you still want to simplify it further, which is Fn over m minus g. So it's either this equation, you stop here, or you can continue with another form, which is this one. Now, what is the velocity, okay, given that condition? What is the velocity in the bottom? Okay, what is the velocity at the bottom? If you want to solve for the velocity at the bottom, then we all know, using this equation again, okay, using this same equation, what is the tangential velocity? So we can say that the tangential velocity is simply equivalent to, or centripetal acceleration is simply equivalent to v squared over r. Now, in order for us to solve for the velocity, the tangential velocity, cross multiplying r and c and take the square root, so your v is simply equivalent to ac AC times r and take the square root on both sides of the equation. So therefore, this should be our equation. However, we all know that AC is simply our Fn over m minus g. Now, what if they want you to express your answer in terms of the normal force, the mass, and acceleration due to gravity? And of course, the r. Next step is to just plug in that value of AC. And our AC should be as simply as Fn over m minus g multiplied by r. So this will be our velocity. So this is the velocity in terms of normal force, the radius, acceleration due to gravity, and mass. This is our velocity in terms of the centripetal acceleration, so on and so forth. Okay, so hope this equation, this step helps, and I'll see you in the next video.